Okay. So this guy wants to have transactional, I guess, disk. Shut up, goddamn bird. This guy wants to have asynchronous disk. Okay. Let's just do a little thought experiment. Who's a better programmer? Somebody who wrote a compiler by themselves, front, middle, and back end, or some who, well, just listen. I'm a better programmer than you. Don't tell me anything making it more like Linux. If you want me to listen, tell me how to make it more like DOS. Okay? You're fighting the last war. You want to make another Linux. There is no market. There is no value in a crappy Linux. There's no value. Okay? There's value if you made a 64-bit DOS that was flat and not segmented, at 64-bit DOS. There would be a market value. The problem is all the were not around for the Commodore 64. They did not learn 6502 assembly. They never saw any other system than the Commodore had. If you typed commands, it went into a basic program in memory, and if you they're just really, they're small-minded, son of a. I can't believe. For someone in the Commodore 64 generation, we did this. At the command line, we said, and the program was in memory. And if we said, if you did that at the command line, it printed, okay? They have absolutely no concept. They're like, where's the path? Where's your include? Where's your... They're so small-minded. I think it's a joke. They can't be that. They can't be that. They're like, there's only one way to do it, obviously. Like, somehow I must... Look, the world is wide open. It doesn't have to be running a file. They think that if you say game, then it's going to search for game in the directory. No, why would it have to do that? It doesn't have to do that. I want to vindicate myself. Let's do that. Vindicate. Okay, so I was a little bit absent-minded when I gave my earlier talk. So, unassemble function sum. Okay, so I meant to say register variable. It has, we're using 16 stack. We're using, each recursion is 16 bytes of stack. It's 64-bit. So we should be able to do some, okay, let's say some 100. We should be able to do some 16,000, I hope. I'm not sure. I'm taking a chance. Let's do 15,000. Okay. So, this person wants it like Linux. No, we're not making it like Linux. Let me tell you how it works, okay? We do not have symmetric multitasking. What we have is master-slave multitasking. What is master-slave multitasking? Multicore. Damn it. Master-slave multicore, something I invented, pioneered, because I'm a genius. Nobody else can think of something obvious like this. They have to think of it. So, this is master-slave multicore. We have a global variable with 64 bits. We have 8 cores. We are going to set MP count is the number of cores. That's going to be 8. So this is 255. We're setting not done is set to 255. We spawn, and then this is the task it runs. This is the argument. It can be anything. This is this is displayed on the this is the task name. It's displayed on the, and this is the core. The core that we spawn a task on a core. So we have master slave multi-core. All applications run on core 0, and they explicitly spawn tasks on the other cores. Okay. Linux wants to be a 1970s mainframe with 100 users and 2 meg of RAM, shared by 100 users with virtual memory and stuff like that. They have a linker that they try to keep everything small. We don't have a linker. We just do everything at once in memory. Anyway, so okay, let's run this. Okay, so standard out is this doc put is basically standard out. It's the document that's the command line. Locked bit test and reset. Let's unassemble a function mp routine. Okay, the simplest way to do semaphores is bit test and set, bit test and reset. Okay, so this is locked bit test and reset. This is a little known assembly instruction. It's an atomic bit test and reset. Okay, we only do one architecture, x86 64. We do it very well. So this is locked bit test and reset. FS is the current task record. GS is the current CPU record. Okay, so if we have a job, let's say we want to. Okay, I'm going to do something silly. No, let's do something not silly. Okay. Let's 1 2 3 1 2 3 1 2 3. That's a billion. Let's go to 10 billion. Oops. We're going to sum the numbers up to 10 billion. So low is going to equal gs num times num divided by mp count. So we're going to take the low end and then the high is equal to gs num plus 1. This is a technique that always works. Well, this is how you divide it up for multi-core. Okay, so let's say for I equals 0, I less than, for I equals low, I less than high, I plus plus, sum plus equals I. Okay, we're not going to use that. We could do the core. Oh, this is just this can be we can get rid of that. We should anyway. Scheist. Okay. Okay, so mp sum equals 0. see if we can get this to work. Okay. So, what we have to do is we have to say lock MP sum plus equals sum. I don't know if this is going to work. Okay, let's give it a shot. Pow! MP sum, we got a negative. How can we get a negative? Oh, that's the float. That's the what? What? We did not print a locked MP sum plus equals sum. Let's try smaller numbers. Sum 1 to 10. 45. I don't know what the answer is. Sum 1 to 3. 3. Okay. Let's go ahead and put this back in here temporarily. Sigh. Okay. So we have %d colon %d to %d comma gs num low high. Okay, let's see about the lock. It did a locked add. It worked. Okay, I haven't tested this very much, so it did a locked add. That's correct. So we can get rid of this. MP sum 3. Oh. We have to say doc print doc. The upper one is a negative. What the truck? Oh, that's a dash. Okay. What? Okay, so this one should take 0. Starts at 0, 1, 2. Okay, so that's the problem. Let's go ahead and make these from 1 plus 1 plus. Okay, 6. That's more like it. Okay, so let's kick this up to 4. It should be 10. Let's kick this up to 5. It should be 15. So let's print n times n plus 1 divided by 2 equals. Now we say num times num plus 1 divided by 2. Okay. 15. Let's do tab. \t colon -t. Okay. Damn it. \t. Okay. Okay. Now let's kick it up to a billion. That's not correct. Why is it negative? 0. You guys got any ideas? Okay. I'm getting nervous. It's not a 64-bit issue, is it? There's nothing 32-bit about this. That looks to be a 32. What the f? What is this number? Let's print it in hex. Oh, maybe it's that. You know, these get pretty big. Oh wait, they should be identical though. That's the only problem. MP sum. Oh, it is. It's a negative. Let's see. What is this? 1, 2. Oops. 3. Oh, it is. Holy shit. We're at the it's a signed. Who let the signed into the party? That's weird. Son of a bitch. Son of a bitch. He's got this bit set. I should know what's going on. You don't suppose this is overflow? What if this overflows? No, it's... Yeah, no. It's exactly off by the sign bit. What? Let's go. I want to do it this way. Hold on a second here. Okay. It's off 11. It has the 8-bit set. What? Why? Lock. What if we let's do an assignment to know what? This is overflowing, as a matter of fact. I thought my MP sum was wrong, but this is the wrong one. You want to know what we can do? Well, okay. So I'm right. I'm right. I'm right. I'm right. God damn it. Okay, what? No, I'm not right. That's not overflowing 2, is it? Divided by 2. That's crazy. That's crazy. What the hell are you talking about? Say what? They're identical. It's overflowing? Is that what? Oh, this is a signed multiply. If that makes a difference. Yeah. Oh, well. A signed multiply? How can we do an unsigned multiply? Oh, let's... What? This is not going to do it. I don't think I don't think it's going to do it. Okay. Let's see if it's let's unassemble. There's a multiply shift right. It's unsigned multiply. Why am I having difficulty with this concept? I should find out which one's correct. What do you think? It overflows by a factor of 2, so that's one whole bit that we're losing. So the top bit is it's too big. It's too big. Okay, that makes sense. So we have one less bit. So even without the sign, well, anyway, okay. Okay, so isn't that cool? So we do master slave. We want to be more. We want to be. Okay, when the Commodore existed, there were mainframes. Somebody decided to make mainframes and play computers into one. Today we have consoles, but that's not the same thing. Basically, white people used to do programming in BASIC, and now the nearest they can come for those kids who are smart is something like Minecraft. But that's just that's a sorry excuse for a BASIC. So the CIA wants the world to be dumb. They want dumb. They don't like Minecraft because that develops the brain, and it's not very good at it. Obviously, there's no compare. I mean, just look at it. If a kid was doing this, that's way more fun. This is like playing with fire. This is awesome. This is what we did as kids, not the goat simulators and first-person shooters. Imagine what's the first-person shooter going to be like in 100 years? It's going to be the same damn thing.